Here are the solutions to L'Hopital's rule day 1. Go ahead and pause the video and check your answers. For some of these, it was asking to just use L'Hopital's rule to confirm what you had to first do on your calculator. Any that required a table, we're not going to worry about those. We'll just always use our calculator right now just to have two different ways to look at these graphically and algebraically. So let's go ahead and take a look. Number 1, we could actually calculate the limit two ways. The first is just going through what we did in the past, which is we could try to factor this. So if direct substitution doesn't work right away, we could try to factor, or now we can use L'Hopital's rule if we're forced or faced with an indeterminate form. So what we could first do, because we will get 0 over 0 if we tried to substitute the 2 in, we could factor that denominator, then the x minus 2 factors divide out, and we're left with 1 over x plus 2, the limit of that as x approaches 2. So now we can substitute the 2 in and get 1/4. Or we could use L'Hopital's rule, take the derivative of the numerator and denominator, which gives us 1 over 2x, and now we can substitute the 2 and get 1/4 that way. All right, for number 2, we're looking at this as sine of 5x. So again, if we substitute in a 0 right away, we get 0 over 0. So carefully using the chain rule here, we're going to get cosine of 5x times 5 over 1, and that's the limit of that as x approaches 0. So I just put that 5 out in front. So now I could substitute in a 0. Cosine of 0 is 1. 1 times 5 is 5. Looking at number 5, again, if we substituted in that 1, we would get 0 over 0. So carefully take the derivative of the numerator. We get 3x squared over 12x squared minus 1 in our denominator. Now we could try substituting in the 1, and we get a 3 over 12 minus 1 gives us 11. All right, and number 6, very similar. Just start by taking the derivative of the numerator and denominator, because substituting in a 0 still gives us that 0 over 0. So here, very carefully though, derivative of 1 is just going to be 0, but cosine x, that derivative is a negative sine x. With the negative that was already in front, we're going to get a positive sine x over 2x. Now, if we substituted in 0 again, we would still get 0 over 0. So this is an example where we have to repeat the process one more time. So now we get cosine x over 2. Now we could substitute in the 0. Cosine of 0 is 1, and we get 1/2 for this. All right, now number 11, that's the one that said to use a table, but you could still do this graphically just to confirm. Like number 2, when we go to take the derivative of the numerator and denominator, because we're still getting 0 over 0 originally, again, that's going to become cosine of 3 theta times 3, and then cosine of 4 theta times 4. So cosine of 0 is just going to give us a 1, and that's how we get 3 times 1 over 4 times 1, so 3/4. So hopefully you guys are doing okay with the problems up to 11. 12 was a slightly different one, the way it was originally written. Our problem here is L'Hopital's rule only works with a single fraction. So that's the clue here. We have to take, right now we're looking at a difference of 2 fractions. We want to merge or get them into one fraction, so we need common denominators. And in doing that, our common denominator is t times sine t. So that means I need to multiply the first numerator by a t, the second one by a sine t. So I get t minus sine t over t sine t. I'm still at 0 over 0 if I were to substitute that in. So I take the derivative very carefully with that denominator though. But up top we're going to get a 1 minus a cosine t. We have to use the product rule down here. So uv prime becomes t times cosine t plus vu prime, which is 1 times sine t. But again, I get a 0 over 0. Cosine of 0 is 1. 1 minus 1 is 0 up top. 0 times cosine of anything is 0 plus sine of 0. So I'm still getting 0 over 0. So I have to repeat the process once more. In doing that, up top, again, derivative of 1 is just 0. Derivative of a negative cosine t becomes a positive sine t. Use the product rule on this. So very carefully we get uv prime, so it's t times a negative sine t. I put the negative out front, plus vu prime, so that's 1 times cosine t, and then plus the derivative of sine t here is cosine t. Now because I do have the 2 cosine of zeros down here, once I do substitute that in, I'm going to get a 2 down here. So I do get a 0. We're not going to get a 0 over 0. We're going to get a 0 over 0 plus 1 plus 1. So we get a 0 over 2, which is just 0. In number 15, this cannot be written as a sine square theta. It's just sine of theta squared in that quantity here. So again, I would get 0 over 0. Theta is just a variable here. So taking the derivative, chain rule, cosine of theta squared times 2 theta, derivative of theta squared, and then it becomes over 1. So now I can substitute in the 0. 2 times 0 is 0 times anything will give me 0 over 1, giving us an answer of 0. And then our last problem that was assigned was number 17. Similarly here, I'm going to get 0 over 0 if I substitute that in. Take the derivative of the numerator and denominator. And please keep in mind, guys, I didn't mention it, but note to still write all the limit as our variable is approaching whatever value in each step until the very last step where we actually do the direct substitution. It's necessary to keep that there. So we get the limit as t approaches 0. We're going to get a negative sine t over e to the t minus 1. But if I substitute that 0 in here, I'm still going to get 0 in the numerator. E to the 0 is 1, 1 minus 1. I still get 0 over 0. So we have to take the derivative one more time. We're getting a negative cosine t over e to the t. This will give me a negative 1 in the numerator. Cosine of 0 is 1, negative 1. E to the 0 is 1, so I get a negative 1 over 1. Or negative 1 as my answer. So hopefully you guys are doing okay with those. Let me know if you have any questions. Let's take a look at some more examples. Here, what I first want you guys to do is get out your calculators, and I want you to graph f of x is equal to sine x over x squared. So go ahead and graph that. Make a sketch of the graph as well. Pause the video while you do that, because I want to know what is the limit as x approaches 0 of this f of x. All right, so hopefully you guys are getting something that looks like this and this. So if we're looking at x approaching 0, we know from, if we come from the right, our graph is increasing without bound. If we come from the left, our graph is decreasing without bound. So right now we would say the left-hand limit doesn't equal the right-hand limit, so overall this limit doesn't exist. But if we took a look at this as one-sided limits, I could show you still using L'Hopital's rule. Let's take a look at the limit sine x over x squared as x approaches 0 from the right. Graphically looking, we know that this is going, it's increasing without bound, so it should give us a positive infinity, but let's algebraically confirm this. So again, I would get 0 over 0 if I substituted this in. So we're going to take the derivative. We're going to get cosine x over 2x. If I substitute a 0 in here, I'm actually going to get a 1 over 0. That's not an indeterminate form, and it's really not 1 over 0. It's 1 over a very small, because if I'm approaching 0 from the right, I'm still positive. Very small positive number, which gives us positive infinity. If we took 1 and divided it, think about like 1 divided by 1/1,000,000th. We multiply by the reciprocal, so we would keep increasing without bound. So that matches what our graph is showing. If we approach 0 from the left, our graph again is decreasing without bound, so we should get a value of negative infinity. So let's take a look at this from the left. Again, taking the derivative, we end up with the same expression. Cosine x over 2x. It's still 1 over 0, but this is 1 over a very small negative number, which is what's going to give us that negative infinity. So sometimes we encounter this. I want to write this out. Please write this down too. So when we reach a point where one of the derivatives is 0, but the other does not, meaning the numerator is 0, but the denominator isn't. We're not getting a 0 over 0, in other words. Then the limit in question is 0 if the numerator approaches 0, meaning it keeps getting smaller and smaller, or either positive or negative infinity if the denominator is becoming a very small positive or negative number. So I'm just going to use capital N for numerator, and our denominator keeps approaching 0, depending on what side. If it's a very small negative number, it's going to be negative infinity. Very small positive numbers can be positive infinity. So that can help us out. In other words, we're thinking of it in terms of words here to help us come up with this. All right, so that's looking as if our limit overall didn't exist. We have to separately take a look at the one limit from the left and the limit from the right. The other indeterminate form we'll be looking at is what happens if we get infinity over infinity. Again, because infinity isn't an actual number, anything involving that could be considered an indeterminate form. There are others, but these are the two, 0 over 0, infinity over infinity, that we'll be looking at. So let's take a look. Limit of secant x over 1 plus tangent x as x approaches pi over 2. So if we think separately of the graph of secant x, go ahead and picture what that looks like, and then 1 plus tangent x. We know tangent x is undefined at pi over 2, but as we're getting closer and closer to it, we keep increasing without bounds, same thing as secant. So right now we actually have the indeterminate form of infinity over infinity because we have asymptotes that we're approaching here. So we're going to use L'Hopital's rule. We're going to take the derivative here. So derivative of secant x is secant x tangent x. Derivative of 1 is just 0. Tangent x, that derivative is going to become secant square x. Now let's simplify this before we try substituting in. So the secant x here, because it's being multiplied, can divide out with the secant x down here, so we're just left with tangent x over secant x. But right now, tangent of pi over 2 is still undefined, so we don't have we can't use that. We have to figure out a way to rewrite this. So this is where all of our identities come into play. So maybe we can rewrite tangent x as sine x over cosine x. Same thing with secant of pi over 2. So we could just write this as 1 over cosine x. And at this point, I mean, we could still simplify this, or you could substitute this in that we know actually cosine of pi over 2 is going to be 0, so we have to go a little bit further here. And this becomes, I'm just looking at the fraction here, sine x over cosine x times the reciprocal of this, so cosine x. So this will just leave us with sine x. So we get the limit as x approaches pi over 2 of sine x. Sine of pi over 2 gives us 1 now. And again, you can graph this original function here and trace it or zoom in until we're right around pi over 2, and then we should be able to confirm this as well. All right, let's take a look at another example. Here, let's say we have the limit as x increases without bound of the natural log of x over 2 times radical x. If you guys want to pause this now and go ahead and try it on your own, but still we're using L'Hopital's rule, so give this a try. No other way to simplify this, so we'll take this limit. Derivative of natural log is 1 over x. Derivative of 2 times radical x, 2x to the 1/2, becomes 2 times 1/2 x to the negative 1/2. So this just leaves us with 1 over x, and then over the square root of x. We could still leave it as x to the negative 1/2. So we could rewrite it this way. It's 1 over x times x to the 1/2 if we just skip that middle step there, rewriting it. So now we could use the laws of exponents here to simplify this. So we actually get the limit as x increases without bound. Subtracting here, our x is greater with the exponent in our denominator, so we actually get 1 over x to the 1/2, or 1 over the square root of x. But looking at this now, again, we don't have an actual number to substitute in. This still will become 1 over, in this case, a very large positive number. So as our denominator is getting larger and larger, our whole fraction is actually approaching 0. But if we went back to the very beginning, we would still get that infinity over infinity as x keeps increasing without bound. All right, let's take a look at just one more. This one again, as x increases without bound, let's do 1 minus 3x squared over 2x squared plus x. In this case, we would actually get a negative infinity in our numerator because it's 1 minus a very large number and then positive infinity in the denominator. Now, we can't say that that's a -1, again, because infinities are not an actual number. So we're still going to go through and take the derivative. So up top, we're just going to get a -6x over a 4x plus 1. We're still at a negative infinity over infinity. So we have to try this one more time. So we're going to get a -6 over 4. Now there's no more variables, so we could just say that this is -3/2. All right, so looking at other indeterminate forms is still applying L'Hopital's rule. So let's take a look here. I still posted in that PDF from the other day the book pages here. So try pages 423, 424, this set of numbers. I'm also going to post as a separate assignment, a separate PDF for this as well, but it's also on my website still. AP page 128, number 6, this deals with slope fields. So I'm going to collect this for a grade. Like I said, I'll post it as an assignment in Classroom. It'll just be worth 9 points, just like the grade on the actual AP exam. As always, guys, let me know if you have any questions.